Now we move on to work, energy and power. So in an isolated system, again, where there is no external force acting, the law of conservation of energy applies. The law of conservation of energy says that the energy is always conserved, meaning that it's converted from one form to another form. It's never created or destroyed. So we will look at this law of conservation of energy in a more detail when we'll cover the topics of kinetic energy and potential energy, and see the conversion of kinetic energy to potential energy and potential energy to kinetic energy. So right now, first we start with the most basic concept called the work done. The work done. So work done. So work is basically done by a force when it moves the point on which it is acting in the direction of the force. So let's say that this is the point and the force is let's say that this is the point and the force is acting in this direction, and this has caused the object to move a particular distance d. Then the work done by this force, work done, is equal to the force times distance. In work done, you have to remember that the force and the distance or the displacement of the particle is parallel, so they both are in the same direction. So here, since the force and the displacement of the particle is in the same direction, we can directly write that work done is equal to force times distance which the object basically travels in the direction of the force. But now let's take the same particle or the point and see when, let's say that force is acting in this direction and the particle is being displaced in this direction. So the particle has moved from A to B with a force which is acting in this direction, and you have to find the work done by the force. So let's take this distance as d. So since force and distance have to be in the same direction, we will have to resolve this force into its two components, fx and fy. And since the displacement of the particle has been taken place in the x direction, the work done should equal the force in the x direction times the displacement of the particle in the x direction. So the force in the x direction and the displacement of the particle are parallel to each other. So if we resolve, so this is making an angle theta. So if we just resolve this vector, this is the horizontal theta, this is fx and this is your fy. Then fx is equal to your f cosine theta. Hence the work done is equal to the fx times d, which is equal to f cos theta times d. So let's take an example. So let's say that you have a particular trolley and this is a rope, and you are applying a force in this direction, and the trolley is moving along the x direction from here to here. So this is the distance, so it's a and b. So what is the work done by the force for moving this trolley from point A to point B? So again, the work done is equivalent to the force times the displacement in the direction of the force. So here you have to apply the same principle. Let's say that this angle is theta with the horizontal, then again your fx is equal to f cos theta, and your work done by the force is equal to f cos theta times the distance covered by the trolley. So for object to do work, what must it possess? It must possess energy. So work is also a type of energy, And now we'll see the work done by an expanding gas. So work done by an expanding gas. And later we'll solve some problems regarding these questions or topics. Expanding gas. So work done by an expanding gas. So let's take a piston and let's assume that this is a frictionless piston and we are applying constant pressure. The pressure is constant in the direction of in this direction, and the piston is filled with some gas, and this is the cross sectional area of the piston. So we know that we are exerting a constant pressure in this direction and gas is filled in the piston, and there's a cross sectional area here, and we in the previous section learned that the pressure due to the pressure is also exerted by fluids, and in fluids we also have the gases. So the gases the gas which is present in the piston has its molecules which are continuously colliding with the cross sectional area of the piston, causing it to produce a pressure at the wall of the piston. So the pressure due to the gas is equal to the force exerted by the cross sectional area. So here we know the cross sectional area of the piston and the pressure. We have to find the force exerted by the gas. So simply rearranging, we get that the force exerted by the gas is equal to the pressure of the gas times the area. So again, the work done by the expanding gas against this constant pressure, the work done by this expanding gas against this constant pressure is equal to the work done by the expanding gas is equal to, again, the force times the displacement in the direction of the force. So we just saw that force exerted is equal to pressure times area. So let's say that if this is the gas and this is the pressure, then there will be certain work which the gas does to push the piston slightly towards the right, and this displacement is x. And if this is x, the height is x, this is the cross sectional area of the piston which is A, then the work done is equal to the force exerted, which is the pressure of the gas, times the area, cross sectional area of the piston, times x. And since we know that the cross sectional area of the piston times the small displacement of x which the gas is doing against the constant pressure is equal to the change in the volume of the piston, we can say that work done by the expanding gas is equal to the pressure due to the gas times the change in the volume which is caused due to the gas on the piston. So while proving this formula that work done by the expanding gas is equal to the pressure against the gas times the change in the volume of the piston, we have made two main assumptions. That the pressure, first of all, is constant, and second, there's constant temperature in the entire system. So in short, the work done by the expanding gas is equal to the pressure times the change in the volume, as we just derived that. So now let's talk about gravitational potential energy. So gravitational potential energy is also a type of work which a force does against the gravity. So let's say, for example, that I have a duster here. So let me just draw the duster. So let's say that this is the ground and this is the duster, and here is one shelf. So I want to place this duster on the top of the shelf like this. So obviously I cannot just say, or I cannot place this duster at the top of the shelf without doing certain work. I'll have to exert a force on this duster through this distance, which is your through this distance. Wait, this is the total distance. So through this entire distance, which we can take it as height, and the force which against which we are doing the work is equal to the weight of the object. So let's say that the mass of the duster is m. So again, work done is equal to the force times the displacement in the direction of the force. So work done is equal to your force, which here in this case is equal to mg, and your distance is equal to your h. Hence the work done is equal to mgh, and this is the formula for gravitational potential energy. Now let's talk about kinetic energy. So kinetic energy is the energy which is possessed by any object which is moving at a particular velocity. It's moving at a particular speed. So let's derive the equation for kinetic energy. So again, let's get back to our basics. Work done is equal to force times the displacement in the direction of the force. Now we know that F is equal to m times a. So if F is equal to m times a and we have got this equation, then substituting ma in your work equation, we will get work is equal to ma times d. Here m is nothing but the force of the here m is nothing but the mass of the object. We can use our Stewart equations, and we can use this Stewart equation which says that v square is equal to u square plus 2ad. So we have got an AD term in the work equation as well. So just substituting the AD value, which is equal to, so AD is equal to 1 upon 2 V square minus U square. In this equation, we get that work is equal to mass times 1 upon 2 V square 1 upon 2 V square minus U square. And assuming that the initial velocity of the particular object is 0, we get that the kinetic energy work done is equal to the 1 upon 2 mass times the velocity squared. So again, let's think about this equation in a bit more intuitive way. So if you have a duster and it's moving at a particular speed which is changing at a constant rate, then the work which is done by this force by placing this duster or by moving this duster in the direction of the force is equivalent to the kinetic energy which the object possesses. Now in the first part of this work, energy and power module, I said that the law of conservation always applies in an isolated system. So this means that let's do the analysis of kinetic energy and potential energy for an object which is on top of a ceiling having height h, and what is essentially happening is that after a few seconds I am pushing this object off the cliff, hence it is falling like this. So when the object is on the top of the cliff, it is stationary, and we said that the kinetic energy is equal to 1 upon 2 mv square. So if v is equal to 0, then at this point, which is the highest point, the kinetic energy is equal to 0. While at this point, it is not such that because the object has no kinetic energy, it does not possess any energy at all. it possesses certain energy due to its gravitational potential energy. And here the gravitational potential energy is at its max, because this is the highest height at which the ball can be placed, and the gravitational potential energy here is equal to mgh. Now slowly and gradually, as you see, your h is decreasing. As your h is decreasing, the object is gaining certain velocity, and as it is gaining certain velocity, its kinetic energy is increasing, and finally at this point, when the height is 0, there is the mgh is equal to 0, and 1 upon 2 mv square is maximum, because at this point the velocity which the object has is the greatest. So this also brings us to one more conclusion, that the loss in kinetic energy is equal to the gain in potential energy. Now let's talk about power. Power is the rate at which the work is done. So it essentially measures the time which the force takes to displace a particular object from one point to another point. So yeah, it just measures the rate at which the work is done. So it is measured in the unit of watt. So it's measured in the unit of watt, and the derived unit of watt is equal to kg meter square second per second cube. So you can just derive this by simply deriving the base or the derived quantity, derived unit of work by the base unit of time. So the derived unit of work is equal to kg m minus 2 times your m upon s, which gives you this. So since we know that power is equal to work done upon time, we have two equations for power. Power is equal to work done upon time. Work done is equal to force times distance. So we just substitute force times distance in this equation. Force times distance upon time. And since speed is equal to distance upon time, or sorry, since here this is essentially the displacement of the particular what do we say, object in the direction of the force, since velocity is equal to displacement upon time, power is equal to your force times velocity. So if an object is moving at a velocity of let's say 5 meters per second, and 10 newton of force is being applied to the object in this direction, then your power is equal to the net force F net times the velocity of that particular object. Now the last part of this section is efficiency. So efficiency of a particular object, or let's say a motor, so efficiency is equal to the ratio of the useful energy output with respect to the total energy input, and efficiency is normally measured as a percentage, hence it is equal to the useful energy output divided by the total energy input times 100. So we will look about we will solve some problems which involve this entire concept of efficiency in the next part of this video. So overall there are a lot of equations in this topic, work, energy and power. So let's just summarize them. So work done by a particular force is equal to the force, the product of the force times the displacement in the direction of the force. The product of the force, the applied force, the product of the net force times the F net times the displacement in the direction of the force. Now work done is a scalar quantity, since it's a measure of energy. kinetic energy is a scalar quantity, gravitational potential energy is a scalar quantity. So work done is equal to work done by a force is equal to our F net times the displacement in the direction of the force. Then the work done by an expanding gas is equal to pressure times the change in volume. Here it is assumed that the pressure acting on the piston is constant and the temperature is also constant. Then the power is we forgot GP and KE. So the kinetic energy is equal to 1 upon 2 mv square. The gravitational potential energy is equal to mgh. The power is equal to the rate at which the work is done, or work done upon time. So work is measured in your joules. So work is measured in joules. So you can try and derive the derived unit of work, which is 1 joule. So power is equal to the rate at which the work is done, which is also equal to your force times the velocity of the particular object. So here the force is the net force acting on the particular object, and the last equation is efficiency is equal to the useful energy output, the useful energy output upon total energy input times 100. Now finally, let's solve a past paper question. So this question is taken from the May-June 2011 edition of the second version first series, and this is the question number 2. So this question states that first it has 3 parts. The first part says that explain what is meant by work done. So work is done by the force when the force moves the point on which it is acting in the direction of the force. You can also write the formula. A car is traveling along a road that has a uniform downhill gradient. So a car is traveling along the road that has a uniform downward gradient. This is 7.5 5 degrees. This is 7.5 degrees, and a car is traveling with a so a car is traveling along a road that has a uniform downhill gradient. The car has a total mass of 850 kg. The angle of the road to the horizontal is 7.5 degrees. Calculate the component of the weight down the slope. So down the slope means that the component of the weight that's along the line of the slope. So resolving this vector, so the weight is equal to your 850 times 9.8. So resolving this vectors into its two component, so first component is perpendicular to the inclined plane and second is along the direction of the plane, and this is also equal to 7.5. Hence the one which is along the direction of the plane is equal to the one which is along the direction of the plane is equal to 850, or your fx is equal to 850 times your 9.8 times sine of 7.5 degrees. So this is equal to 1090 newtons. The force which is acting down along the line of the inclined plane due to the weight of the object is 1090 newtons. Now the third part of this question says that the car is traveling in B. The car in B is traveling at a constant speed of 25 meter per second. The driver then applies the brakes to stop the car. The constant force resisting the motion of the force is 4600 newtons. So the force which is resisting the force which is resisting the motion of the force is 4600 newtons. So show that the deceleration of the car with brakes is equal to your 4.1 meters per second. So right now the car is traveling at a constant speed of 25 meter per second. So at this point, the acceleration of the car is equal to 0. But then when he applies the brake, the resistive force is greater than the um, applied force, which here is due to the weight of the car. Hence, the net force along the x-axis, the F net, is equal to your resistive force here, which is 4600 minus 1090, which is equal to your 3510 newtons. And since your sigma F is equal to ma, 3510 is equal to 850 times a, hence a is equal to a is equal to 4.1 meter per second. Now let's do the second part. The second part states that calculate the distance the car travels from when the brakes are applied until the car comes to the rest. So when the brakes are applied, it's a constant deceleration of 4.1 meters per second. So since it's a constant deceleration of 4.1 meter per second, we can use our Stewart equations. So our Stewart equation says that v square is equal to u square plus 2as. But here a is essentially negative. Hence, your final velocity when it stops is 0 is equal to your 25 square minus 2 times the deceleration times the distance. Hence, if you solve for s, you will get 676 meters. Now the second last part of the question says that the loss of kinetic energy of the car is equal to 1 upon 2. So the loss of kinetic energy of the car is equal to 1 upon 2 mv square. So 1 upon 2 mv square, which is equal to 1 upon 2 the mass of the car times the velocity of the car, which is 25 square, which is equal to 2.7 into 10 raised to 5 joules. So this is the loss in the kinetic energy. So now the work done due to the resistive force for moving this object 76 meters is equal to the magnitude of the resistive force 4600 newtons. So work done is equal to force times the displacement in the direction of the force. So it's equal to 4600 newtons. So it's equal to 4600 newtons times 76, which is approximately equal to 3.5 into 10 raised to 5 joules. And the last part asks us that why are these two quantities not equal? So the simple answer is that this is the work done due to the resistive force, which is the 3.5 into 10 raised to 5 joules, and this is the loss in the kinetic energy. Hence the total loss in the total energy is equal to the work done by the resistive force, and this is only the loss in kinetic energy. But since it's moving in an inclined plane, it also loses some potential energy. Hence the difference is equal to the loss in the potential energy.